your last trip, did you discover what the Earth people eat? They eat a great many of these. They peel them with their metal knives. Boil them for 20 of their minutes. Then they smash them all to bits. They are clearly a most primitive people.
Scholars also knew that the Earth wasn't flat. The scholars also knew that the Earth wasn't flat. As well as navigation, astronomy was also important for the measurement of time. For example, the Islamic calendar is a lunar calendar where the months are determined by the phases of the moon. During the Golden Age, astronomers studied the movements of the moon to predict the calendar more accurately. The 12 months making up the Islamic year are shorter than the Earth's orbit of the sun. So, Islamic months and religious observances like Ramadan move from year to year.
The Greeks believed that the Earth was at the centre of the solar system. And in order to make the mathematical model fit the observations of the way in which the planets appeared to move on the sky, they had to put all these ridiculously complicated features into the model.
It got very, very messy, circles within circles going around other circles.
It did, yeah.
And that's where Tusi's genius comes in, because this diagram, the Tusi couple, simplified a lot of that. If I show you what's supposed to happen, you see this small circle going around the big one. If you trace a point on the perimeter, it's moving up and down in a straight line. And that turned out to be a very useful trick that simplified a lot of that complicated maths.
Yeah.
But what's really fascinating, compare this text written in Arabic with this one. It's an identical one, but written in Latin. And what's fascinating is the letters labeling the points follow the Arabic alphabet, not the Latin alphabet. So Alif, Ba, Jim, Dal, A, B, G, D. Clearly, whoever drew this knew about Tusi's work and the Tusi couple. Well, the man who drew this was Copernicus.
So this is Copernicus who came up with the idea that rather than the Earth being at the centre of the solar system, it was the sun at the centre, and all the planets, including the Earth, revolved around it.
Revolved around it, and that's the picture that we have today. Copernicus was and is regarded as the father of modern science because of this great revolution. And yet what's so fascinating
is that this was built on Tusi's ideas.
Yes, so it shows the continuity of science. Copernicus owes this debt to these medieval astronomers from the Golden Age.
That's incredible.
Scholars also knew that the Earth wasn't flat, which direction Mecca was in order to face towards it during prayer. Now, during the early days of the empire, it wasn't so large and this wasn't a problem. The scholars of the Golden Age were very proficient at map making. But as the empire grew and stretched from India in the east all the way to Spain and Andalusia in the west, it was much more of an issue, because the scholars also knew that the Earth wasn't flat. Now, why does this matter? Well, if you were, say, a Muslim in Cordoba, then facing towards Mecca, if you just looked at a flat map, would involve pointing roughly southeast. But on a globe, it's different. If I attach this string, one end to Cordoba and the other to Mecca, then you see the line actually takes you east to begin with and then curves down to the southeast. So it's not at all obvious without understanding that the Earth is a sphere. This meant that these scholars had to develop an area of mathematics called spherical geometry, which was exceptionally advanced for 1,000 years ago. But to use this spherical geometry, scholars first needed to know the size of the Earth. The ancient Greeks had provided several estimates of this. Their method was clever but crude. It involved measuring the angle of the sun at a particular time of day and then walking in a straight line in a particular direction until that angle changed by 1 degree. All they then needed to do was calculate how far they'd need to walk for the angle to change by 360 degrees. That would give them the circumference of the Earth. The early 9th century Abbasid Caliph al-Ma'mun wanted to improve on this estimate, so he commanded a group of astronomers to repeat it. However, the method involved them trudging through the desert for over 100 kilometers, a method that was prone to error. 200 years later, in the 11th century, the Persian astronomer al-Biruni came up with a much easier and more accurate method of estimating the size of the Earth. But it did involve climbing a mountain that looked out over the horizon. Al-Biruni was a prolific scholar who even debated about whether the Earth was moving. He explained how to work out the size of the Earth in his book on the determination of the coordinates of cities. First, he measured the mountain's height. Al-Biruni then had to climb to the top of the mountain, and armed with an astrolabe and a plumb line, he then measured the angle of dip from the horizontal down to the distant horizon. Now, this was just half a degree, so he had to be incredibly precise. But armed with this information, he could then use some more clever geometry to calculate the circumference of the Earth. Let me show you. Imagine this circle is the Earth, and this is Biruni's mountain. Now, looking across horizontally, he measured the angle of dip to the horizon, this angle here. Now, if you draw two lines, one through to the center of the Earth from the mountain and the other from where the line touches the horizon, you end up with a right-angled triangle. Now, Biruni knew that the angle he'd measured is the same as this angle inside the Earth. Armed with these two pieces of information, the size of this angle and the height of the mountain, he was able to use geometry to work out the radius of the Earth. Multiplying this number by 2 pi gives him the complete circumference. He got to within 1% of the accurate value we know today, about 40,000 kilometers, which is pretty remarkable.